Good morning for everyone. My name is Gintaras Valušis. I'll be chairman of the session. It's my honor and big privilege to introduce Professor Chennupati Jagadish from Australian National University. And initially, I will say some words about scientific career. Jagadish received bachelor degree from Nagarjuna University in Guntur, India in 1977, and Master of Philosophy and PhD degree he received from University of Delhi in 1982 and 1986, respectively. Then he worked as a postdoc in Kingston University, in Queen's University in Kingston, Canada. And then in 1990, he moved to Australia and established a major program dedicated to semiconductor optoelectronics and nanotechnology. Currently, he's a distinguished professor and head of semiconductor optoelectronics and nanotechnology in Australian National University, director of Australian National Fabrication Facility. Professor published nearly 1,000 research papers, and about 700 of them are in research journals. He holds many honorary positions. I would like a big list, and we mention only several of them, like visiting professor at Oxford University, Leverhulme visiting professor at Cambridge University, honorary professor Nanjing University in China, fellow of School of Engineering of University of Tokyo, visiting professor at Anna University, Mangalore, India, and distinguished and young professor in Institute of Chemical Technology, India, and distinguished chair professor for research, National University of Taiwan. So many work distinguished, illuminating technology and fantastic results. And today, title of the lecture is Semiconductor Nanostructures for Optoelectronics Application. We expect a nice talk and dedicated to science, beauty, and import of semiconductor nanostructures, and in particular nanowires. So Chennupati, it's your words. Thank you for your time and efforts to participate in this conference. Please.
Thank you very much, my friend Professor Gintaras, for that kind introduction. And it's really a pleasure to be in Vilnius virtually. And I would simply say to all my friends in Lithuania, labas rytas, and good morning. And it's great to be here. As been mentioned that I'm going to really talk about semiconductor nanostructures, mainly focusing on nanowires for optoelectronics applications. There's also been mentioned that in addition to having the positions position at the ANU, I have honorary positions in India and Japan, China, Taiwan, US, and UK. It's a really pleasure to work with people in various parts of the world and my colleagues in various parts of the world, because the beauty of science is that there are no national boundaries. By working together, we can make much bigger progress. And so that's what really excites me in terms of doing science. Before I proceed further, I would like to acknowledge my collaborators in various parts of the world. And really today's talk is a collaborative effort between my group at the Australian National University and many groups in Australia, US, UK, China, Sweden, Italy, Russia, Switzerland. So really, again, because of the fact that the science is has no national boundaries, and then really working with my colleagues in various parts of the world is really great fun for me. And also many students and postdoctoral fellows in these groups have really contributed to our research as well. I want to thank all of them. Without their contribution, really nothing much to talk about. So this is my group at the Australian National University. And so really, typically we got 10 to 12 nationalities. And so it's a really pleasure to work with my colleagues. And then again, their hard work and passion is the one leads to some beautiful results, which I will share with you. I also want to take this opportunity to thank our funding agencies for their support for our research and allowing us to be able to have fun. So here is an overview of my talk, and then I'll really talk about why we are interested in semiconductor nanowires and semiconductor optoelectronics. And then I'll mainly be focusing on nanowire growth and some nanostructure growth. And then we're talking about nanowire lasers and LEDs and terahertz detectors, nanowire solar cells, nanowires for neuron growth. We also work on terahertz modulators and nanowires for photoelectrochemical water splitting, but I'll not have time to really talk about these two topics. But if any of you have any specific interest, please feel free to send me an email and I'm happy to respond to any questions or direct you to our papers in those particular topics. Before I proceed further, I would like to thank many groups, those who are working on the field of semiconductor nanowires in various parts of the world. And in science, we learn from each other. So it's very important for us to make sure that we acknowledge our colleagues, those who are contributing to the fields which we are working in. I want to thank all my colleagues, those who have for their contributions for enriching the field of semiconductor nanowires. Before I proceed further, I would like to really introduce, before going to nanowires, I just would like to mention about our new Center of Excellence in the Transformative Meta-Optical Systems. As most of you know, that the industrial revolution started with steam power mechanization. Second industrial revolution started with electrical power, mass production. Third industrial revolution started with automation and computer power. Fourth industrial revolution, and people are predicting that the digital world and the biological world will be coming together. And then we'll be using light to sense and interface humans and machines because of the fact that the 80 to 90% of our information is obtained through light. So light-based technologies are currently about $1 trillion Australian industry's value, but people are predicting by 2030 or so that this industry will be doubling or so. World Economic Forum has identified many technologies which are needed for the future, and they include holographic displays and wearable optical sensors, light navigation and communications, including LiDAR and autonomous vehicles, and 3D vision and gesture recognition, enhanced machine vision and augmented reality. All these aspirational technologies require fundamentally new approaches for smart and miniaturized optical systems. And then that's what we are really trying to develop as part of our Center of Excellence. And which has been led by my colleague, Professor Dragomir Neshev, and we are really trying to make use of the nanostructures and the metamaterials to be able to generate light, manipulate light, and detect light. So really, it's an exciting program for 7 years. It's only started in January this year. In fact, we have got about 15 CIs involved in this particular project, involving 5 universities in Australia. Also, another 20 PIs are involved from various parts of the world as well, international collaborators participating in the center. We're looking for some PhD students and postdoctoral fellows. And then if you're looking for a PhD positions or postdoctoral fellows in this area, please keep an eye on our website and then apply for those positions. In fact, at the moment, there's an advertisement has been released that there are 4 postdoctoral positions that are available at the ANU. I want you to apply for those positions if you've got the right qualifications. So now let me move towards optoelectronics. So what is optoelectronics? All of you know that optoelectronics is, a wide variety of structures. For example, the conversion of light into electricity using photodetectors or solar cells, or conversion of electricity into light, like LEDs and lasers and other things, for example. So those are the optoelectronic devices. Either you're converting electricity into light or converting light into electricity. As most of you know that the silicon is a workhorse for the microelectronics industry, but unfortunately, silicon is not a very good light emitter. And so, because it's an indirect bandgap semiconductor. And because of that, and you need to really find materials which are direct bandgap semiconductors which can emit light efficiently. That's where the group 3-5 semiconductors come into picture of the gallium arsenide, indium phosphide, gallium nitride, aluminum nitride, indium nitride, gallium antimonide. Combination of these materials have got different band gaps, the energy difference between the bottom of the conduction band and the top of the valence band, and then different materials emit different colors of light or detect different colors of light. So that's why we're interested in exploring different materials. For example, the nitride semiconductors developed by our colleagues from Japan, and then Dr. Amano and Akasaki and Nakamura, who developed the blue LEDs, which were a missing link till that point about 20 years back or so, that led to major developments in terms of solid state lighting and white LEDs. And they won the Nobel Prize for 2014 for physics, for example, due to the development of the blue LED, which was a missing link among the primary colors. Once you got all 3 primary colors, you'll be able to make white LEDs. And in fact, solid state lighting and large area bright displays are all been developments due to the developments in this blue LED technology, along with already existing green and red LED technology or so. So the same materials which are used for making LEDs can also be used for making lasers. And so again, we work on both LEDs and lasers, and I'll come and share with you some of the developments of how we are making use of these materials for making these nanowire lasers and detectors. But also it turns out that today I'm able to talk to you through optical fiber communications, through internet. So the electrical signals from my computer have been converted into an optical signal by using lasers, and they get modulated and sent through optical fibers. And on the other end, and these things are getting converted, the optical signals are converted into electrical signals by using photodetectors, for example. And typically they are operating at 1.3, 1.55 micron window region. That's a region where optical fibers have got the lowest absorption and dispersion. So indium gallium arsenide phosphide material system is ideal materials for these things, and that's what we work on as well. But also the photodetectors, and again, the same materials could be used for photodetectors, infrared detectors, which are used in biomedical imaging applications and night vision applications, and even in manufacturing to look at the light, the heat generation in the computer chips while you're operating them, taking infrared images of these ones, so that you can redesign the computer chips so that you can minimize the hotspots. Heat dissipation is a major issue in the computer chips. But also same materials are used for making most efficient solar cells. In fact, high efficiency solar cells with exceeding 47% have been developed by using multi-junction solar cells. And these are developed for the space applications, but now people are also exploring how it can use them for concentrated photovoltaic systems. So let me come to nanowires. Why are you interested in nanowires? Nanowires are seen as building blocks for the next generation electronics and photonics. One of the unique things with the nanowires is that if you got a material which got a large lattice constant or a small lattice constant with respect to the substrate, they can expand or contract without creating dislocations. So whenever you're dealing with the two-dimensional materials, you always have to worry about the lattice constant of the layer which you're depositing, what's the lattice constant of the substrate. Because of their nanoscale and three-dimensional architecture, in principle, you should be able to grow nanowires of any material on any substrate without the constraints of lattice mismatch. So if that is the case, and then in principle, we should be able to integrate three-phase semiconductors, optoelectronics technology, with silicon, with the microelectronics technology, which people have been working in this area for a long time. Defects have always limited this, and then now we and other groups are working on trying to integrate 3-5 nanowires on silicon. You can also create heterostructures within the nanowire. For example, this green material is different than the red material. So that means you can create quantum wells or quantum disks and all these things, for example. You can also create PN junctions within the nanowire. So that means you can be able to make a single nanowire based lasers and LEDs and solar cells also, which are photodetectors and other things which I will come back to. You can also create radial heterostructures, core shell nanowires. This red material is different than the pink material or so that means you can create a multi-layer structures also. You can also create the branch nanowires, and which allows us to be able to make three-dimensional architectures. In fact, these are some of the examples in our own laboratory where we're able to show that you can make gallium antimonide on top of gallium arsenide. Despite large lattice mismatch, we're able to show that you can get atomically perfect gallium antimonide nanowires on top of gallium arsenide nanowires. You can also create indium arsenide branch nanowires on top of gallium arsenide. So that means you can really use them for cantilevers and scanning probes and other things. You can also create nano trees of indium phosphide, which could be used as for energy harvesting applications. For example, for splitting of water to generate hydrogen, where different parts of the nano trees absorbing different parts of the solar spectrum, for example. And most recently, we are going from nanowires to nanomembranes, which I will come back and then share with you. But most importantly, International Technology Roadmap for Semiconductors, and these are the people, those are determining what technologies are needed for the next generation electronics. They've identified nanowires as a key technology component for electronics as well. And so if the lattice mismatch is no longer an issue, can we really grow 3-5 nanowires on silicon? And in fact, IBM Zurich has demonstrated indium gallium arsenide nanowire transistors on 6-inch wafers of silicon. It demonstrated excellent results from that one, indicating that nanowires are going to play an important role both in electronics and photonics, for making LEDs, lasers, photodetectors, biosensors, and so on and so forth. Okay. So if the nanowires are so much of importance, how do you make these ones? There are two main techniques which we use, and one is called as a metal catalyzed VLS growth process. Another thing is called selective epitaxy. So in this case, we take metal nanoparticles of gold, for example, of 50 nanometers in this particular instance, and gold has got a melting temperature of more than 1000 degrees Celsius. But once the gold reacts with the gallium or aluminum or indium, the alloy melting temperature comes down to as small as 350 degrees Celsius. So now if you put this wafer, which of gallium arsenide, for example, with gold nanoparticles into an MOCVD reactor, metal organic chemical vapor deposition, there's also alternative technique called molecular beam epitaxy. You can use either of the techniques to be able to make nanowires. You put this one into the reactor and heat it to somewhere between 370 to 500 degrees Celsius. Then what happens is that this gold is reacting with the gallium and gallium arsenide. It starts forming into this gold gallium eutectic liquid at around 350 degrees Celsius. So now we've introduced the gases needed for the growth of gallium arsenide, trimethyl gallium and arsenine in the case of MOCVD, and gallium and arsenic in the case of MBE. They get incorporated as liquid alloy, it gets supersaturated, crystal starts precipitating out, and gold is always sitting on the top. It is like putting sugar into water. If you keep on mixing more and more sugar, above solubility limit of the sugar, what happens is sugar crystals start precipitating out. The same physics is happening here as well. So in fact, this is a work of my former student and who is now an associate professor at Cambridge University, Dr. Hannah Joyce. And then she developed a technique called a two-temperature growth process, where she was able to demonstrate we can get really beautiful cylindrically shaped nanowires with no defects whatsoever. Scanning electron microscope image of these gallium arsenide nanowires, which are about 50 nanometers in diameter. And then also you can see the gold nanoparticle sitting on the top and gallium arsenide nanowire sitting at the bottom here, indicating that we can really control the dimensions of these nanowires by essentially changing the diameter of the nanowire which we are using here. This is an example of a 50 nanometer nanoparticle which Hannah Joyce happened to use. So because we're incorporating a vapor into a liquid and getting a solid, and then Wagner and Ellis and Bell Labs in 60s, they call this process called as a VLS growth process. So the alternative technique is called selective epitaxy. In this case, we don't use any metal nanoparticles. We deposit some silicon dioxide by PECVD process, plasma enhanced chemical vapor deposition, and then put some photoresist or ZEP resist for electron beam resist, and then do electron beam lithography and transfer those patterns through silicon dioxide by wet etching so that you can expose indium phosphide in this case, and then other parts you've got silicon dioxide is covering that. Then you put this one into the MOCVD reactor, heat it to somewhere between 62 to 750 degrees Celsius, and then introduce the gases needed for the growth of indium phosphide, trimethyl, indium, and phosphine. These gases dissociate, and then nanowires beautifully grow here. There's a work of Dr. Chian Gao, who is a research engineer, and Dr. also Aruni Fonseca. Dr. Chian Gao is in Blue Glass in Sydney in a company. And Dr. Aruni Fonseca is at Warwick University in UK. You can see that because we created ordered patterns of these structures, you can really get these beautiful ordered patterns here. You can also see beautiful hexagonal facets because these nanowires are growing along 111 crystallographic orientation. That's the lowest surface energy orientation of these structures. So we've taken these indium phosphide nanowires and looked at the light emission from these structures by exciting them with a laser pulse, essentially photoluminescence characterization, and where we measure the quantum efficiency as a function of the excitation power. And you can see that you can get up to 50% quantum efficiency in these nanowires. And we compared the performance of these nanowires with the epitaxial layers, which are grown under optimal conditions. And the blue curve here, they both are very much comparable, indicating that in the case of indium phosphide, surface non-rate recombination is not significant because it's got the lowest surface recombination velocity of any of the semiconductors, which I know of, for example. So these nanowires are very good for making lasers and solar cells and other things, which I will come back to. So then we asked ourselves, instead of opening a hole, what will happen if you open a slot or a ring in these masks which I talked about, silicon dioxide mask, and open a hole in the middle, for example, or or a slot or a ring. This is the work of Dr. Nayan Wong, who just completed his PhD. Again, he spent about 4 years in order to be able to optimize various growth conditions to be able to really grow these structures. So here's a case when Nayan Wong opened a particular crystallographic orientation of 101 bar, this slot, and then he puts into the immersibility reactor, introduces the heated to 650 to 750 degrees Celsius, which is the gases needed for growth of indium phosphide. And then you can see that you can get a beautiful membranes in this case with this particular facet, sidewall facets in this case here. But if you open the slot on another crystallographic orientation, 112 bar here, and again you can get membranes here, but in this case the facet is different because of the changes in the crystallographic orientation. And then if you open the slot in between these two crystallographic orientations, you can get these beautiful diamond-like structures with these alternating facets of these 101 bar 0 and then 112 bar 0 or so. So now we can see, instead of just making nanowires, and then we can start making nanomembranes, which are thin or thicker membranes, or otherwise diamond-like structures. It really opens up a lot of opportunities for us to be able to really make exotic structures using this selective epitaxy technique or so. What will happen if you open a ring? Again, the Nayan Wong has done that one, and you can see that you can get these beautiful alternating facets of these two facets which I talked about, and you can really start growing beautiful rings here. And in fact, we keep on growing. What happens is that you end up creating this membrane with these alternating facets again. If you keep on growing further, ultimately you finish off with these nice hexagonal facets. And because of the fact that they are the lowest energy facets, crystal facets, and crystals always likes to be in the low energy facet state or so, you can create a beautiful membranes of wide variety of shapes, which could be used for a range of applications. So Nayan Wong has taken these structures and looked at the cathodoluminescence from these structures. See, here's the top view of these nanostructures of the nanomembranes, nanodiamonds, and nanorings. And then in the case of cathodoluminescence, instead of using lasers, we use electron beam to excite the electron hole pairs and look at the light coming out of these ones. You can see you get a very uniform light emission from these nanomembranes and nanodiamonds and nanorings, indicating that we're able to, Nayan Wong is able to really get excellent quality nanorings and nanostructures with no defects. And if there are defects, and they'll end up getting a non-uniform light emission. And the uniform light emission is a good indication that we managed to get very good structures or so. So now, in fact, we're using these nanorings, for example, ring resonator lasers, for example. In fact, a new student, Wei Wong, who started a PhD a couple of years back, he's recently demonstrated ring resonator lasers or so, which I'll not have time to talk about. So till now, I talked about materials, but now let me move towards the optoelectronic devices. Ultimately, the people want to know what type of devices you can make out of these ones. So all of us have studied about lasers in our optics courses, undergraduate optics courses. You need to have a gain medium. You need to have a laser cavity with two mirrors here, for example. You need to pump the gain medium and then create population inversion. And as and when the model gain in the laser cavity is equal to the optical losses, then the lasing starts taking place also. So, okay. This is a threshold condition for lasing. Again, this equation is essentially telling the same thing. And model gain need to be equal to the optical losses in the cavity, then only lasing starts taking place. So if you take, it turns out if you take a nanowire, and if you shine light from the top, light starts coming from the both ends of the nanowire acts like a waveguide. And this is something, of course, you need to choose the right kind of nanowire and dimensions and other things, which I'll come back to. But also because of the large refractive index difference between the nanowire, which is 3.4, and then the air refractive index of 1, and then both ends of the nanowire acts like mirrors. So I really do not need to create any external mirrors or anything. If I design these things correctly, each nanowire should act like a gain medium because I'm using direct bandgap semiconductors, and both ends of the nanowire act like mirrors. So that means in principle, each nanowire should act like a laser. So if I get everything right. Okay. So in fact, we have been working on making wide variety of nanowire lasers. And I see this is Dr. Dhruv Saxena, who is at Imperial College in UK now. He's demonstrated first gallium arsenide nanowire lasers. Dr. Chian Gao has demonstrated first wurtzite indium phosphide nanowire lasers. And also Dr. Dhruv Saxena has demonstrated multi-quantum well nanowire lasers. And Dr. Tim Burgess, who is at IP Australia now in Australia, And he has demonstrated zinc-doped gallium arsenide nanowire lasers or so. But I'll not have time to go into the details of all of them. I'll just give you one or two examples. So here is a case of the Dr. Drew Saxena's work, where he has shown the light propagations of these nanowires, and he looks at a wide variety of optical modes which are propagated with these nanowires. And here's a case where he's showing TM01 mode, which has got the highest field intensity here, and in a 260 nanometer gallium arsenide nanowire, and then he shows that light is propagating to these ones. So in fact, he has done calculations of the threshold gain needed for making these lasers to work, and as a function of the diameter of the nanowire. And you can see that the smaller the diameter of the nanowire and the threshold power needed, the gain needed to really make these lasers to work is very, very high. That means before even you start being able to make these lasers to work, and the material damage takes place, and then these nanowires never will be lasing. If the diameter is below 200 nanometers or so, you can see you need to go to very high threshold powers, gains you need to have. In fact, I'm not plotting from 0 nanometers here. I start only plotting from 150 nanometers here. But also this is dependent on which optical mode is lasing as well. You can see typically 250 to 300 nanometer diameter nanowires for a nanowire of about 10 microns long, sitting on a glass substrate, is the ideal diameter for to be able to make these things to lasers. So again, simulations are really playing an important role, and we do the FTDD simulations, finite difference time domain simulations, mainly use numerical, for example. Is a peak gain as a function of the injected carrier density. Again, carrier density, higher carrier density is needed if you're operating these lasers at a higher temperatures or so, which again shows that it's important for us to be able to do these calculations and designing the right kind of devices in order to be able to make these lasers to work. So based on Drew Saxena's calculations, Dr. Jenny Jiang, who is at Cambridge University now, she has grown these gallium arsenide, aluminum gallium arsenide core shell nanowires of about 6 microns long, transfer them onto a glass slide here. And Drew Saxena did these measurements, and he excited the laser pulse and look at the light coming out of these ones. You can see that a very broad light emission below threshold, you can see here as well. And above threshold, you see a very sharp light emission. That's what you would expect from a laser. You can also see the output versus pump intensity. You can see the nice threshold-like behavior here. And a log-log plot of this output power versus pump intensity shows this S-type behavior, which is confirming that the true lasing is taking place of the structures. You can also see beautiful interference fringes coming from when these nanowires are lasing. And Drew Saxena, in fact, has done simulations to compare the interference fringes you expect from a 6 micron long nanowire with respect to the measured ones, and he is able to compare these theoretical simulations with experimental results very well. And these are the first nanowire, gallium arsenide nanowire lasers operating at room temperature, published about 7 years back or so. This really created a lot of excitement in the community, ability to be able to make these gallium arsenide nanowire lasers, because surface recombination velocity of gallium arsenide is very high. So that's where we really need to do some surface passivation and all sorts of things, and also get high quality nanowires as well in order to be able to make these nanowire lasers. So by the way, just to give you an idea of the dimensions of these lasers, and typically I can put about 10 to 20 lasers within the width of your hair. That tells you how tiny these lasers are. So what are we using these lasers for? So in fact, this is a collaborative work with my colleagues at University of Strathclyde, Professor Martin Dawson and Professor Antonio Hurtado and Professor Michael Stein's groups. And there they developed something called nanoscale transfer printing technique. In this case, they come up with a PDMS stamp, and they can pick up the nanowire laser or any nanowire, and they can drop them wherever you want, precisely. So this is a work of research fellow in their group, Dr. Ben Wilhaber, and he spent a lot of time in the lab to be able to optimize these conditions. So here is a case where you can see that these nanowires have been transferred onto flexible glass so that we can use things for flexible optoelectronics applications. You can see the optical image of these nanowires here, and then they pump them and then look at the light emission. Again, you can see that the light is coming from both ends of the nanowire. You can also see the threshold-like behavior and also very sharp light emission, indicating that this transfer process is a gentle process, and we have not created any damage during this transfer process from these nanowires from one substrate to another substrate, which is looking very promising for a wide variety of applications, for example. So they have been able to couple these nanowires to the light coming from these nanowires to an optical waveguide. This is an SU8 polymer waveguide, so that you can really do the couplers, for example. You can couple the light and multiplexing and demultiplexing applications, for example. They were able to show that you can couple the light efficiently. You can see the laser 1 and laser 2 in front of these two waveguide branches here. And they're able to show on the other end, you're able to see the light emission from these structures, for example. Okay. So that means whenever I want to be able to couple the light into an optical waveguides, I can be able to make use of these edge emitting lasers because these nanowire lasers act like a fabric cavity, for example. So then we asked them, can you be able to couple these nanowire lasers with the nano antennas using this nano transfer printing technology? There's a work of Professor Fang Ren. She's at Nanjing University now, and then she worked in my lab for some time. And she has been designing these terahertz metamaterials. So what she has got is the nano antenna of aluminum. There's this, they call them as a bullseye antennas, and then there's a gap in the middle. And then we requested our colleagues in Strathclyde that whether they're able to locate these nanowires in the middle here. You can see that they're able to locate these ones very nicely. You can see the close-up of this one here. This is a nano antenna here, and then here's the nanowire here. If you do not have any nano antenna, light is coming from the both ends of the nanowire because of the fact that the nanowire is acting like a fabricated cavity. I have shown you the information about that simulation earlier. And then, of course, if you put this nanowire into nano antenna, suddenly light is coming from the vertical direction because we're able to engineer the radiation patterns. So that means we're able to suddenly make vertical emitting nanowire lasers. Again, you can see the threshold-like behavior, sharp light emission, and indicating that really they were suddenly got these vertical emitting nanowire lasers. And these are very interesting for being able to make two-dimensional arrays of nanowire lasers, for example, for facial recognition applications or meta-optics applications or coupled cavity lasers and a range of applications. So if I want to couple the light through an optical waveguide or something, I can use an edge emitting laser like this one here. And whenever I want to use it for vertical emitting lasers, and I can use these nano antenna combination lasers, depending on the applications, you can make use of them for various applications. Again, these are the world's first vertical emitting nanowire lasers or so. Again, this we published about 3 years back or so. So till now, I've only shown you optically pumped lasers. So I have not shown you any electrically pumped lasers, but ultimately industry wants to see electrically pumped lasers because most of the time when you're using lasers, they are electrically pumped, but not often you use them for optically pumped lasers, for example. This is a work of Dr. In-Suk Yang, and then he's came from Samsung, and then he has gone back to Samsung as a research engineer now. He has done this doping of this indium phosphide with a P-type doping of zinc, and then he has grown indium gallium arsenide quantum well here, and then he put this N-type indium phosphide on top of that. He spent about 2 years in order to optimize these conditions in order to be able to grow the quantum wells and get the P-type doping right and N-type doping right. Then he transfers these ones onto a glass substrate and then do electron lithography and makes contacts to these things using gold titanium contacts at the both ends of the nanowire here, for example. You can see the IV characteristics showing like a diode-like behavior and then indicating that he's able to really get a good PN junction here and also that he can able to make good ohmic contacts and other things. So he injects the current into these nanowires and then look at the light emission from these ones. You can see that as you're injecting the more and more current, you can see that the light emission is increasing, intensity is increasing as a function of injected current. You also see 2 emission peaks. It's mainly because of the fact that you got one actual quantum well here, one radial quantum well there. The thickness and composition of this indium gallium arsenide is different for the radial quantum well to the actual quantum well. So that's why you end up getting 2 emission peaks. But fortunately, the light emission peak is taking place in the 1.3, 1.55 micron window region. That's a window region which is important for optical fiber communications. So you can see that though light intensity is increasing, but there's no narrowing of the line weight, no threshold-like behavior from this output characteristics here, indicating that they're acting like a light-emitting diodes, not like lasers. So the question is why? You got a PN junction, you got all the metal contacts, you're injecting current, but why you're not able to make them to laser? The main reason is that when you put metals to inject current into these nanowires, and these metals have got large optical losses. So that means essentially you're creating a lossy optical cavity. If you want to get over those optical losses, you should pump them harder. If you're pumping them harder, you're generating a lot of heat. That means the gain goes down, and you have to even pump them harder. It becomes like a vicious circle or so. So now we got a new student, Nikita Kagrani, and then she is now trying to design new structures without putting metals, like putting some indium tin oxide and other transparent conducting oxides, trying to make ohmic contacts with these nanowire structures in order to be able to really get these nanowire lasers to work, electrically pumped nanowire lasers to work. And I'm hopeful in a year's time also I'll be able to share those results with you. And in fact, she has been working for the last 3 years on this project. Still, there are many challenges in order to be able to make these things to work. Okay. So now, of course, instead of using single nanowires, before finishing of his PhD, Insuk again tried to make nanowire arrays. So these nanowires are grown vertically, and he fills this with the polymer material. He selectively etches using plasma etching of this polymer, exposes the tips of the nanowires, put some indium tin oxide on the top, and put some metal contact at the top and the bottom, and then he injects current and then looks at the light emission. You can see the IV characteristics showing that the diode-like behavior. Again, as and when you're injecting more current, and you can see the intensity of the light is increasing. In fact, you can even see the close-up of this particular thing under the probe. You can see very bright light emission coming that he is able to make these nanowire LED arrays, for example. So why are we interested in making LED arrays? But it turns out that if you can embed these ones into polymer materials, you can peel these things off. So that means they could be very useful for foldable displays. For example, Samsung and Apple and others are interested in foldable phones and foldable laptops and other things. So you need to have foldable displays, and that's why Insuk has focused more on this developing this LED technology for that particular application or so. And though the wavelengths which we are using are different here, but ultimately people want to really make them into the visible region, and that's what he's working on. So now let me move from lasers to and LEDs to terahertz radiation. And as all of you know, that there's a big gap between electronics and photonics. In electronics, we go from microwaves to millimeter waves. In the case of photonics, you go to the visible region to the infrared region. There was a gap called terahertz gap for many years. And then now, during the last 20 years or so, many groups have been developing terahertz technology, including my colleagues in Lithuania. And so then my good friend, Professor Arnas Krotkus, has been working in this area for a long time. 1 terahertz is about 300 microns in wavelength. And why people are interested in terahertz radiation? And the beauty of it is that many chemical molecules have got fingerprints in the terahertz parts of the electromagnetic spectrum. And also that the terahertz radiation is reflected by metal, so that means they can be used in the airports and other things for metal detection. Also, terahertz radiation is a non-ionizing radiation. So unlike X-rays, which create DNA damage, and terahertz radiation doesn't create any DNA damage, for example. They could be used for biomedical imaging applications, looking at the cavities in the teeth, or for wireless communications, or even looking at the water content in leaves, so that you only water the crops whenever they need to be, though that thereby you're not wasting your precious resource like water, for example. So really, we've been working with this one with my colleagues at Oxford University, Professor Michael Johnson and Professor Laura Hertz's groups there. And this is the work of my student, Dr. Kun Pan, who is now a postdoctoral fellow at Oxford University. She has really taken one of these nanowires and transferred them onto a quartz substrate. Quartz is transparent to terahertz radiation, and made some electron beam lithography contacts here. And then she connects this one to an emitter, for example, here. He shines the light laser onto the nanowire, and then you generate electron hole pairs. And then you come up with the terahertz pulse. Electric field of the terahertz pulse is the one which separates the carriers between the two contacts. You can measure photocurrent as a function of time. If you can measure the current as a function of time, you can get the information about the electric field of the terahertz pulse and also conductivity of the material which we're dealing with. And Kunpan, during her PhD, developed a wide variety of gallium arsenide nanowire terahertz detectors and then indium phosphide terahertz detectors. But to cut the long story short, let me share with you her most recent results, which we have published last year. And then she developed these polarization resolved terahertz detectors. By using these Baute antennas and then placing these nanowires in orthogonal direction, and then thereby you could measure both X and Y polarization of this terahertz pulse, for example, here. She spent about 3 years and working with my colleagues in Strathclyde University and then be able to develop these things. And you can see the close-up of these structures, the nanowires and then about the antennas. The challenge has been the nanowires on the top should not be in contact with the bottom nanowires. And that's where she had to spend a lot of time in optimizing the fabrication conditions, for example. So again, what are we making use of these polarization sensitive detectors to really determine the properties of the terahertz metamaterials, for example. You create a terahertz metamaterial, and then you send a terahertz pulse to this one. And then, of course, terahertz pulse is interacting with the metamaterial, and its polarization properties change. And by using our detector, we're able to measure both and X and Y polarizations. So here is a case of the close-up of these terahertz metamaterials she has designed and fabricated. And theoretically, she's simulated and then expected that X polarization will have this transmission characteristics, Y polarization will have this transmission characteristics. And here are the measured ones using our terahertz detector, polarization sensitive terahertz detectors. These are the room temperature operating, polarization, phase, and amplitude sensitive terahertz detectors. So now this opens up opportunities for us to be able to create high resolution terahertz imaging systems and other things which my colleagues at Oxford University are working on. Let me now move towards the nanowire solar cells. Nanowires are again opening up opportunities to be able to make solar cells. And whenever you make solar cells, you have to really make p-n junctions and you make it thick enough to absorb all the light. And that means carriers need to migrate more large distances, contacts are at the bottom and the top, and you lose some of these carriers when you say that the solar cell is 20% efficient, and 80% of the carriers are lost for defects at surfaces or impurities, for example. But in the case of nanowires, you can make the nanowire as long as you want to absorb all the light. You can make a core cell p-n junction, so thereby carriers can be collected efficiently. So that means you're able to decouple the light absorption pathways and carrier collection pathways. Also, these nanowires can act like light funnels because of the high refractive index of the nanowires. Light always likes to be in the high refractive index medium, for example. But also they act like a low reflection. They also got low reflection losses, so that means you don't need to put any anti-reflection coatings on it. So we've done extensive simulations again. What should be the height of the nanowire? What should be the diameter of the nanowire? What should be the distance between the nanowires? You can see that the most of the current is generated at the tip of the nanowire, indicating that you don't need to make a long nanowires. 1 or 2 micron nanowires are sufficient. This is an example for a gallium arsenide nanowire or indium phosphide nanowire, for example, in this case here. We've also gone and looked at the diameter of the nanowire, and then again, optimum conditions are the highest current you get is for nanowires which are about 150 to 160 nanometers in diameter, and diameter to pitch ratio, pitch is the distance between the nanowires, is about 0.5 or 0.6, for example. You can see, and 0.5, 0.6 is the maximum current being generated here. Again, these simulations play a very important role in making any of the devices in using these nanotechnologies. So here's a case where, again, we have grown these structures of this schematic here, and then the gallium arsenide, aluminum gallium arsenide nanowires. And then also these are the, with the fill this with the polymer material and selectively etched, as I mentioned earlier, like we've done for LEDs, and put some indium tin oxide and put some contacts at the top and the bottom, and then shine light and look at the current generated from these solar cells. Again, to cut the long story short, and my colleagues at Technical University of Eindhoven, Professor Rick Barkers and also Professor Rick Garnett, FOM Institute in Amalfi, have demonstrated 17.8% efficient solar cells. And these are some of the most efficient solar cells reported in the literature to date, which looks very promising for future applications, for example. So we have been working with our colleagues with Professor Laura Hertz at Oxford University. Instead of using polymer materials, we are trying to replace the gaps in this thing with the organic semiconductors so that we'll be able to use this as a flexible solar nanowire solar cells, because you can peel these things off very easily. So that means you can, in the future, you can have solar cells can attach to your backpacks and other things, and then be able to really provide you the power needed to be able to charge your electronic devices and other things, for example. So let me finish off with my last topic of the brain repair. And this is the work of my young colleague, Dr. Vinny Gautam. All of us know that we got 80 billion neurons, and then their neurons form into these neuronal networks. So whenever you got a brain damage, essentially you're breaking this neuronal network, and then you lose some of the functions. You cannot move, or you cannot talk, or you cannot eat, or some problem or the other. if we can we really create a neural patch and be able to make the connections back? This is a question which we asked ourselves. And then if you can make these connections back, and hopefully you can be able to give the functions back to people. Again, Vinny has spent a lot of time in really growing these neurons on the indium phosphide nanowires. You can see neuronal cell body here, soma, and then these neurites really follow these patterns of these nanowires beautifully here. You can see some of the dendrites which are coming of these things. So for example, these could be axons or any other neurites which are really following these patterns beautifully. Instead of using a single neuronal cell, what will happen if I use multiple neuronal cells? So that's what Vinny has done. And she's put multiple neuronal cells in this box where this region is the one where indium phosphide nanowires are. You can see a wide variety of cell body of these neurons. And these axons are really following beautifully and making connections of this pattern here. If the neurons are outside the nanowires, you can see that they are making random connections. There's no pattern whatsoever here. So what Vinny does is something called a calcium imaging. In the case of calcium imaging, he puts a calcium dye. As and when the neurons are really firing action potentials, and they're opening up of the ion channels and calcium ions are passing through those ones, the amount of calcium ions concentration will determine the fluorescence intensity of these the calcium imaging technology which people use. So then she does the correlation maps. If this neuron is firing, what's happening to this neuron and this neuron, and this neuron, these astrocytes, and then be able to really try to study and what type of interaction is taking place. So she tries to compare these ones, nanowires, neurons grown on nanowires, and also neurons grown on plain glass substrates. So here's a case where the neurons which are on glass substrates change in fluorescence as a function of time. You can see that the neurons which are grown on glass substrates, they're all firing randomly. There's no correlation taking place, and a very low correlation coefficient here. But whereas when the neurons are grown on indium phosphide nanowires, you can see the change in fluorescence as a function of time. They're all firing at the same time. You see excellent correlation, indicating that we got some sort of a synchronized and correlated activities taking place on the neuronal network which we've grown on these indium phosphide nanowires. And Vinay Gautam has presented this work at a neuroscience conference a couple of years back. And so then these neuroscientists were asking the question, what neurons you're growing? And she mentioned that she's using rat neurons, and they said, why are you wasting your time? How about using human stem cells? So now we got a project funded by the Dementia Australia and Yulgil Bar Foundation, and where we are working with stem cell biologists and taking the stem cells from the Alzheimer's patients and creating some mini brains or organoids here, and then studying the signaling behavior so that you'll be able to really learn from the signaling behavior using also artificial intelligence techniques, developing algorithms, deep neural networks, and with the hope that we'll be able to learn from these things and then use the algorithms developed from the healthy people and stimulate the Alzheimer's neurons with the hope that we'll be able to get the functions back. We're also creating neuroelectrodes to be able to measure the neuronal signals directly from the brain. So really an exciting development, an exciting project. And I'm learning a lot because I don't know much about stem cell biology or neurobiology or neuroscience. And it's really a multidisciplinary project involving Melbourne University, Monash University, Wollongong University, and the ANU. With that, and in conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale and developing new class of lasers and LEDs, terahertz detectors, integration of optoelectronic devices on various platforms, and nanowire solar cells, engineering of growth of the neuronal networks. But I didn't have time to talk about modulators, terahertz modulators, or PEC water splitting. And let me finish off with some information. And I'm currently serving as editor-in-chief of the Applied Physics Reviews, which is one of the highest impact factor journals in applied physics of 17.05. If you got any breakthrough results or any exciting new reviews which you want to write, and please submit your articles. And our current rejection rate is about 90%. We only select of them. So only submit when you got a breakthrough results. And as I mentioned, that our Center of Excellence is looking for PhD students and postdocs. And also my wife and Vidya and I have created an endowment for supporting students and young physicists from the developing countries to come and spend some time at the ANU for up to 3 months or so that we can open the doors for people from the developing world, because I started my life in a very small village in India, and so many people helped me, including my high school teachers and others, and as a gratitude to all of them, we started this one so that we'll be able to support the next generation of young scientists also. With that, thank you for your attention, and I'm happy to answer any questions you may have.
Thank you very much for beautiful and amazing talk. I mean, now it's open for discussion and questions. So, who wants to ask Professor about beautiful physics behind this technology? Yeah. No question. Okay, I'll start myself then. You shown very nice. Okay.
Yeah, go ahead, Gintaras. Go ahead, please, go ahead.
Okay, so you shown very nice technological picture on indium phosphide nanowire, and it was a plot dedicated to quantum efficiency. Pretty nice curve. Question is, then it goes to when you increase excitation power, it means it goes. It seems to me that it goes to saturation. Could you comment on that? Is it theoretical limit or something in physics, or or simply technological reasons because of surface recombination, something like that? Just would be interesting to know.
So it is much more of a theoretical limit than the surface recombination, but it turns out indium phosphide surface recombination velocity, in fact, we measured that one using terahertz spectroscopy, and that one has 170 centimeters per second, which is about 4 orders of magnitude lower than gallium arsenide, for example. If I take the gallium arsenide and then I try to measure the lifetimes, for example, typically I measure picosecond lifetimes, but in the case of indium phosphide nanowires, typically I measure nanosecond lifetimes, which are very much comparable to the excellent the epitaxial structures which are grown in ideal conditions of them. So of course, basically what happens is that essentially you're really creating that, because the number of states which are available there are small because of the small volume of the material, you end up saturating that particular emission process. Okay, so otherwise indium phosphide is a very good material. You don't have to worry too much about surface recombination. But whereas if it is gallium arsenide, and that's a major issue, that's where what we have done is that we tried to grow the aluminum gallium arsenide shell surrounding the gallium arsenide. By doing that one, you're creating a potential barrier for carriers to go to the surface, and that's able to make these nanowire lasers or solar cells. Because otherwise, you can never make the bare gallium arsenide nanowires to lasers. But whereas the bare indium phosphide nanowires, without any surface passivation, we're able to make them lasers, for example.
Okay, thank you. So I see some questions are coming from chat. So the first one is, what are the key features that may be considered or taken into account for future nanolaser applications? And the second one is, if we compare obtained lasing threshold on different nanowires, what's the conductor material is the best choice to start with a nanolasing fabrication?
Okay, so let me start with one by one. And then by the way, these nanowires have got a very high confinement factor, which is because of the high refractive index. And that's why where you're putting these nanowires becomes an important thing. We transfer them onto glass slide because glass has got a low refractive index of 1.45 or so. But whereas these materials have got 3.4 refractive index, so that means the field is confined to the nanowire. Okay, so that's why these nanowires, nanolasers, wherever you need a nanolaser, we'll be able to provide them using the nano imprinting technology, for example. For example, you want to use it for sensor applications, or otherwise, coupled to an optical waveguide and be able to use it for a wide variety of other applications, like flexible optoelectronics applications and other things. You should be able to make use of those ones. That's our aim, to be able to make these things. But the is also that the power from these nanolasers is not too high. So when you're really trying to use it for high power lasers, these are not the ones which you should be using. Wherever you want to use them for compact applications, for example, people want to use nanowire lasers in cells, for example, so that you can get a coherent light emission to be able to really image these things much better and other things. So these lasers are ideal. For example, of course, you need to make sure that the materials are biocompatible. For example, indium phosphide is a biocompatible material. In fact, we try to grow the neurons on gallium arsenide substrates, and these neurons don't grow and they start dying. But indium phosphide turns out to be very good biocompatible material, just for a given example. In terms of the lasing thresholds for different nanowires, and then it turns out that whenever we are breaking these nanowires from the substrate, the top facet is really flat because of the fact that you got a crystal facets. When you're breaking it, what happens is that it breaks at the random points. That means that particular facet is not very highly reflecting. Also depends on where it is breaking, how it is breaking, what its shape, and all these things. In fact, my former postdoctoral fellow, who is a lecturer in University of Manchester now, Dr. Patrick Parkinson, has developed a technique where he can measure thousands of lasers very, very quickly. Means within, means a few seconds, he'll be able to, each laser he only takes about 5 seconds or so something. So his group is able to really create a binning technique of being able to put which laser has got a high threshold, which has got a low threshold, and other things. In fact, that's what my students in China are doing. Whenever they make LEDs, so they do the entire wafer mapping, and then really try to pick up the ones which are high brightness ones, put into a bin which requires for high brightness applications, and then which are the ones which are from the periphery, they end up using for low brightness application, for example, toys or indicators and other things. So depending on what applications you have, you can make use of that one. In terms of threshold powers, I think indium phosphide is a better material than gallium arsenide because of the surface recombination and other things which I talked about.
Okay. And
in order to be able to pump the area of the nanowire, start lasing uniformly, sorry, there's another question as well. So that's why what you use that we use a cylindrical lens so that you'll be able to pump the nanowires uniformly. If you don't pump them uniformly, what happens is that you got the absorbing region and then the gain region. So it becomes a really challenging thing, and that's what helps us to be able to do that. Please go ahead.
Thank you. And I have another one. You talked about a nice detector for terahertz. So in fact, nanowire as a terahertz detector. So questions for you: how you manage two competitive things in like in gallium arsenide? You need short lifetime and relatively high mobility. So how you can manage in your delicate technology? It's tricky. It should be tricky.
Yes. So, but most interestingly, as you know, that we have been working on the ion implantation and annealing of these things. And of course, my friend Arunas does all these low temperature gallium arsenide growth and all. And so in fact, we have done early work on this implantation induced short lifetimes with Arunas. In fact, we published lots of applied physics letters and along with Maria Kaminska, and then we used to call as APL collaboration, Australia, Poland, Lithuania collaboration sort of thing. And we used to publish lots of APLs in 90s or so. So now coming back to your question, it turns out that because of the fact that the gallium arsenide has got a very high surface recombination velocity, and then because the surface is nearby, so then we end up getting a short lifetimes. But if we can get rid of the defects in the nanowire, and then they get also very good mobilities. In fact, we measured the mobilities of these nanowires using terahertz spectroscopy. In fact, that's how we got the idea of making the terahertz detectors, because we are using ensembles of nanowires to be able to make these optically pumped terahertz spectroscopy to measure the conductivity as a frequency and all these things. We measure the mobilities. Mobilities are looking more than 1,000 or 2,000 or so per cm square per volt second. And then they got very short lifetimes. That's how we started really working on these ones.
Thank you.
So we end up getting excellent gallium arsenide nanowire detectors. And also we have extended that one to indium phosphide as well. But in the case of indium phosphide, because of the fact that they got long lifetimes, they're called as integrating terahertz detectors, and you have to do the differentiation afterwards in the signal processing after measurement of the signals or so sort of thing. We made use of both the technologies, either direct detectors or integrated detectors. Very good question.
And there is one question also in the chart, so about comparison of parameters of quantum dot and quantum wire laser. Could you comment shortly?
Quantum dot and quantum wire lasers, could you? Okay. We in fact used to do a lot of work on quantum dot lasers, quantum wire lasers, and now we're going for nanowire lasers. But if I'm making a quantum dot laser, remember that you still need to have an optical cavity, and you need to have all these, waveguides and all these things. In fact, that's what we have done in 2000s or so, demonstrating indium arsenide quantum dot lasers, InGaAs quantum dot lasers, gallium arsenide nitride quantum dot lasers, and other things. But in this case of nanowire, the beauty of it is the compactness of these nanowire lasers. You can really make, 6 micron long laser. And if you would have told me 20 years back, you can make a laser which is only 6 micron long, I would have said, no way. But now we're able to do that one because of the excellent quantum the optical confinement in these nanowires, and also excellent quality of these nanowires as well, and which is allowing us to be able to do that one. But again, as I emphasize that, if you want to use for a high power lasers, and you still need to go for a quantum dot and quantum well lasers. But if you really want to go for, you don't need very high powers, but what you need is a coherent light source. And then nanowire lasers are very attractive. So depending on what applications you have to choose the right kind of laser for those applications. Because we work on a multiple device technologies, then that gives us the opportunity to be able to say which one is better than the other, rather than claiming that, oh, my laser can do everything. Only one laser cannot do everything. Okay, that's a good question as well.
Thank you. Thank you for a fascinating lecture, for your time being with us and sharing your knowledge and experience. Thank you. Thank you very much.
No, thank you very much. It's always a pleasure. And I hope I was able to come to Vilnius last year, but I had to cancel the trip in the last minute. We were able to meet virtually.
Yeah, really. Thank you. Thank you so much.
Thank you.